Welcome to 2-Minute Anaesthesia in Critical Care. Today we're going to investigate the mechanisms of gastric acid production, regulation, and the effects of pharmacological regulation of these pathways. First of all, it's important to define gastric fluid or gastric juice, which is a thin, watery, acidic digestive fluid secreted by glands in the mucous membrane of the stomach. We will now discuss the functions of gastric fluid, which is twofold. Firstly, protection. The high mucus component within the fluid is rich in bicarbonate, which lines the stomach, preventing gastric erosion from the acidic component. It also has immune and exocrine functions. Secondly is digestion. It's able to digest both macro and micronutrients. Macronutrient digestion involves pepsin, which is involved in protein breakdown, and lipase, which hydrolyzes the ester bond in triglycerides. But also micronutrients. Intrinsic factor binds to B12, creating a complex which can be absorbed in the terminal ileum. The gastric mucosa secretes approximately 1.2 to 1.5 litres of gastric fluid per day. Gastric fluid contains 5 key components, mainly water, which is 96% by weight, intrinsic factor, a selection of enzymes, including pepsin and lipase, a mucus, which is rich in bicarbonate, and a selection of electrolytes, including chloride, sodium, hydrogen, potassium, and calcium. These include chloride at a concentration of 100 to 150 millimoles per litre, sodium at between 20 to 80 millimoles per litre, and hydrogen between 40 and 60 millimoles per litre. As we've mentioned, the stomach has a range of functions, and therefore there's a range of different cell types. Today we're going to discuss parietal cells which secrete hydrochloric acid. The location of cell types within the stomach varies, but as we've mentioned, parietal cells are located in the upper 2/3 of the stomach. Parietal cells secrete hydrochloric acid by a relatively complex mechanism. First of all, it's important to note that the hydrogen concentration inside the parietal cell is greater than 1 million times that of the plasma, and therefore this is an active process. We'll now discuss the mechanism. Carbon dioxide and water are able to fuse passively into the parietal cell. They react in the cytoplasm to produce carbonic acid in the presence of carbonic anhydrase. Carbonic acid then dissociates to produce hydrogen and bicarbonate ions. The hydrogen ions then cross into the stomach lumen via the hydrogen-potassium ATPase for exchange with potassium. This potassium then moves back into the stomach lumen via a potassium exchanger across the apical membrane. Now let's look at the blood side of the cell, i.e. the basal membrane, where bicarbonate is exchanged for chloride. The chloride then moves across the cell and crosses the apical membrane into the gastric lumen via a chloride transporter, and thus forming hydrochloric acid. As you can see, there are 3 receptors on the basal side, CCK2, H2 and M3, which bind gastrin, histamine and acetylcholine. These are involved in gastric acid regulation and will be discussed next. The key regulators in gastric acid production are shown, those which increase gastric acid production, acetylcholine, gastrin and histamine, and those which reduce are somatostatin. This is not an exhaustive list, and there are other regulators, but these are the key basic regulators. We will now look at the gastric acid stimulation factors, and this occurs in 3 phases: cephalic, gastric and intestinal phases. The cephalic phase, i.e. sight, taste and smell of food, activates the vagus to secrete acetylcholine, which binds to the basal membrane of the parietal cell. Next is the gastric phase. Gastric distension also stimulates the vagus nerve, which increases acetylcholine production. Interestingly, the composition of food can lead to direct activation of G cells which secrete gastrin, and gastrin binds to CCK2 receptors and thus enhance gastric acid production. And finally, enterochromaffin-like cells in the stomach secrete histamine in the presence of gastrin and acetylcholine, which bind to H2 receptors on the parietal cell. And lastly is the intestinal phase. This has a small effect on gastric acid production, however, duodenal distension can activate G cells. Now we can see a simplified diagram of the parietal cell with the positive green stimulation factors shown. It is now widely accepted that the ECL cell activation is the most important physiological pathway, as it has multiple inputs from other pathways. The G cells are located in the lower stomach and secrete gastrin. The gastrin moves into the bloodstream to the upper stomach, allowing direct activation of CCK2 receptors on parietal cells and indirectly onto ECL cells. Binding to ECL cells increases acid production via histamine release, as the histamine binds to the H2 receptors on the basal membrane. The enteric nervous system innervates the upper stomach, mainly via the vagus nerve, which produces acetylcholine, which binds to M3 receptors directly on parietal cells and indirectly onto ECL cells, which also increase histamine release. A range of drugs can be used to modulate these pathways. First of all, the vagal pathway can be modulated by atropine, resulting in a 70% decrease in acid production. And H2 receptor antagonists can attenuate histamine binding and thus reduce acid production. Finally, PPIs inhibit the final step, the hydrogen potassium ATPase. Now we can look at the factors which inhibit gastric acid production. As mentioned, these affect three pathways: cephalic, gastric, and intestinal phases. Feeling full or satiety can reduce vagal activation. If the gastric pH drops too low, this can result in D-cell activation and thus somatostatin release in order to balance degree of acid secretion. And finally, the intestinal phase. If the fluid bolus has a very low pH or excessive irritation of the mucosa, this can lead to a reduction in vagal activity. Now we can see the red inhibitory pathway is simplified. So D cells produce somatostatin, which is the main inhibitor of acid secretion. Somatostatin binds to the SSTR2 receptors on the parietal cell, which inhibits acid secretion, but also SSTR2 receptors on ECL cells, which reduces histamine release from that cell and thus reduce gastric acid secretion. The vagal tone is also reduced, which has less acetylcholine effects on the M3 receptors on both ECL cells and also parietal cells, and thus reduce gastric acid secretion.